So we're going to start proving some properties of homomorphisms to try to get better at checking if things, for example, are monomorphisms and so on. But we're also going to try to illustrate that we actually have a good definition. It's one thing to make a definition of what sort of the right interaction between rings should be, or the right interaction between objects and whenever you're studying. It's another thing for that definition to actually be useful. So what does it mean for the definition to be good or the right definition? Uh, maybe good and right aren't the right words. Maybe skillful is the right word. So what does it mean that the definition is skillful? It means that ring homomorphisms should preserve ring theoretic properties, right? If these are supposed to be structure preserving maps, well, it should preserve structure. So the next series of theorems that we're going to go through is to give evidence to that. So our first theorem is, suppose we have a ring homomorphism, then phi preserves 0. So it sends 0 to 0. And if you take a moment and you look at the definition of a ring homomorphism, you'll notice that that is not a condition there. At no point is that condition written there. So this is not by definition. We actually have to go in and we have to prove it. So let's do that. All right, so let's notice that 0 plus 0 is 0. Brilliant. This is a very useful tool when you do these simpler proofs, and it's useful in general. And so what this tells us then is that phi of 0 plus 0 is phi of 0. But phi is a homomorphism, so it breaks up under addition. So this uses the fact that we preserve addition. But we have a phi of 0 on either side, so we can go ahead and we can subtract phi of 0 from both sides, or add the additive inverse, however you want to say it. And when we do so, on the left, that becomes a 0, and on the right, that becomes a 0. But a 0 where? A 0 in S. Great. So phi preserves 0. Let's go in and let's prove another theorem. I'm just going to say phi r to S is a ring homomorphism. In fact, I'm just going to say ring hom. Then phi, well, how am I going to say this? Then if U is a unit, phi of U is also a unit. Oops. But in S. All right. So what this is saying is phi preserves units, or phi preserves multiplicative guys that have a multiplicative inverse, which is another ring theoretic idea. Proof. Well, since U is a unit, there exists V, not necessarily, well, it's also going to be a unit, but there exists V in R such that UV is VU is 1. And again, I'm not assuming commutativity here at all. Then phi of UV is phi of VU is phi of 1. Well, phi is compatible with or preserves multiplication. So each one of these breaks up under, each one of these products breaks up under phi. Lastly, phi sends the 1 to the 1. So here we've used preserves times and 1. So phi of U has a multiplicative inverse. Phi of V is the multiplicative inverse. Oh, so phi of U is a unit. Fantastic. So it preserves units. And the last thing we'll prove to give more evidence that phi is structure preserving is that phi sort of sends powers to powers. So phi is compatible with powers. So suppose, again, phi from R to S is a ring Hom. Then for all n and n, and A and R, phi of A to the n is phi of A to the n. Now, why should this be true? Well, whole powers are repeated multiplication, and phi is compatible with multiplication. So it should be compatible with powers. Nevertheless, we need to prove it. So we're going to proceed by induction because it's a statement about all natural numbers. The base case is n equals 1. And that is phi of A to the 1, which is just A, is phi of A to the 1. But of course, this is true. This is just phi of A is A. This is true. So to that end, we're going to suppose that it's true for n minus 1. That is, you can bring the power outside for n minus 1. And we show that phi of A to the n is phi of A to the n. All right. So how do we do that? Well, we were going to write out our phi of A to the n. And we're going to write that as phi of A times A to the n minus 1. Trick that you can use always is to separate powers to strip off one, as we did when we talked about divisibility. Now, phi is compatible with products, so we can break this up under the times. The second term here, by the induction hypothesis, the power comes out. But that's n phi of a's. Great, so let me write the left-hand side in now. That checks out. So this completes the proof by induction. Okay, so we saw that phi preserves the additive identity, it preserves units, it preserves powers. In fact, if A happens to be a unit, so A to the negative 1 makes sense, you can combine these and show that phi actually preserves all integer powers, which is something that I leave to you. Maybe I'll assign it as an exercise. But nevertheless, phi is compatible with a lot of the structures that we've, with a lot of the usual structure with rings. So this is laying evidence, it is giving evidence at least to say to the statement that phi is a good definition or is a skillful definition of a structure preserving function.